So let's look at question number 9 on page 113. It says, based on figure 7.25, what is the minimum speed v that the mass must have in order to make it to position B? So I'm going to read this as we're going to go from here up the hill to A and then down to B. So what is the speed we need at V to be able to get all the way to B? A is going to be 4 meters high off the ground level. B is going to be 2 meters high off that ground level. And then what speed will the mass have at B? And then part B just gives us an initial velocity and then trying to find the velocity at A and B. And so when we look at A, like we're going to be like, man, there is nothing. They don't give us anything. They give us height and that's it. They don't give us mass. They don't give us some initial velocity. And so, that can be pretty frustrating at first. But if we can set up the problem and work through it, we'll see how we shouldn't need those other things. So let's set this up. Initially, what we're going to have here is we're going to have all kinetic energy. So that's going to be greater than 0. And then our gravitational potential energy here would be 0, and that's because I'm going to say this is a height of 0 down at the bottom. And then there's no spring throughout this, so there's going to be no spring energy. Where right here, we're going to say the energy potential gravity at A is going to be greater than 0. And I'm going to say the kinetic energy is essentially really, really close to 0. I'm going to say it's going to be equal to 0 at A. And then B, we're going to say, there is some potential energy greater than 0, as well as my kinetic energy is going to be greater than 0. So that's how I'm going to say this. And some people might not like this idea of, well, kinetic energy 0, well, then it's not moving, and how's it going to get across to A? But I'm going to say that's going to be the minimum, right? If it's any faster, it's going to be able to just barely slide across A and then get down to B. So if we're looking for this idea of a minimum, right, the extreme would be when kinetic energy is maybe not equal to 0, but essentially 0, right? Really, really, really close to 0. So we can just imagine that it is 0 then instead. So here's how I'm going to set this up. So for part A, we're going to first set up our energy equation. And that's going to look like, okay, initially I have kinetic energy, and then that has to be conserved, so I'm going to have potential energy due to gravity, and then I'm going to have potential energy, and this is going to be at A, potential energy gravity at B, plus the kinetic energy at B. So here is position A, or my start, right? Here is position A, and here's position B. And again, the conservation of energy says that these things, the energy at each position has to be conserved as long as there's no work done. And, I don't read any friction or any air resistance. So we're just going to say all three of those are equal. So we could then rewrite this as the idea of 1/2 mv, let's say u, right, u squared equals mg h of A, which is going to equal mg h of B plus 1/2 m v b squared. And so when I look at and it says what's the minimum speed in order to make it to position B, I'm just going to focus on this first part because we know we know G is a constant, we know H, and then M here can cancel out. So if we rewrite this, 1/2 mu squared equals mg h A, right? And really we're just trying to, find u. So m's cancel out, and then I'm left with 1/2 u squared equals GH of A. Multiply each side by 2. I get u squared equals 2GHA. And then obviously we need to square root that. So it's going to be the square root of 2 times 10 times 4. So that's the square root of 80, which is going to be 8.9 meters per second. So that's the minimum speed. Again, any faster than that, and we're going to be successful regardless. And then B, or the second part, it says what speed will the mass have at B? And so we can again, for the second part, I'm going to take this part. We know G, we know H, and we don't know V. I'm going to take this part because let's just imagine maybe we got this answer wrong. We can still take this second part. So now with this, what I'm going to do is I'm going to find V at B. And that's going to be MGHA equals MGHB plus 1/2 MVB squared. Masses go away. And we get GHA equals GHB plus 1/2 VB squared. So I'm going to subtract GHB from both sides. And then I'm going to rewrite this as 1/2 V squared equals GHA minus GHB. So what I'm going to do is I'm going to factor out my G's here, and then I'm going to also multiply each side by 2. And when I do that, I'm going to get V squared equals 2GHA minus HB. Square root, both sides. And I get that the velocity at B is equal to this 2 times 10, square root of 4 minus 2. So that's what? 2 times 10 is 20, times 2 is 40. So that's the square root of 40. So my velocity at B is going to be 6.3 meters per second. All right. So again, it can seem scary if we can just get our initial setup of, what's the energy at each position, then even though it doesn't give us any numbers, we should be able to work through the problem because it's just, this is our main key. We got to get this set up, and then we can plug in our, what each thing is, and then we should be able to solve for whatever we need. For part B, it says if the velocity is 12 meters per second, what will the speed be at A and B? So again, this is going to be where we're going to start. And now, so for B, we're going to find velocity at A and velocity at B. And my equation now might look a little different because now I'm going to have kinetic energy initial equals the potential energy of gravity at A plus kinetic energy at A. And I'm saying this because, if it's asking us to find V at A, then there has to be some kinetic energy equals gravitational potential energy at B plus the kinetic energy at B. That's going to be 1/2 mu squared equals mgha plus 1/2 mva squared equals mghb plus 1/2 mvb squared. So to find VA, I'm going to use this one, find VA. Again, I'm going to do it without any numbers first because we can get rid of things. Our masses go away, so it doesn't matter what the mass is. And then we're left with 1/2 u squared. I'm going to subtract this over, minus GHA equals 1/2 VA squared. Multiply each side by 2. Twos get rid of there, and we're left with VA squared equals u squared minus 2GHA, and then we need to square root that. So VA equals my initial velocity, which is now 12, I believe. Yep, that's 12. So that's going to be 12 squared minus 2 times 10 times 4, and that's all square rooted. So 144 minus 40 minus 80 square root. So that's the square root of what? 64. And the velocity at A then would be 8 meters per second. No calculator needed. Lastly, then let's do the same thing for velocity at B. With that, I'm just going to use this relationship to these. It's just, less stuff to plug in, less work. So if this equals this, this also equals this. So kind of skipping a few steps, what I should be able to do is I'm going to get rid of my masses. I'm going to get MGHB on the other side. So I'm going to start with 1/2 mu squared minus MGHB equals 1/2 MVB squared. Again, M's go away. Multiply each side by 2. And write VB squared over here. That cancels with that. So that's going to be u squared minus 2GHB. The beauty of it is it looks the same, right? That's the cool thing. This and this, they're the same. The difference is this is the height at A, this is the height at B. So what do we got? 12 squared minus 2 times 10 times 2. Square root that. That is 144 minus what? 20 times 2 is 40. That's the square root of 104. Which is going to get me a value of 10.2 meters per second. All right, and those answers should make sense. At B, I should have a higher velocity. At B, I've gone back down the hill, so an answer at 8 and 100 or 10.2 work out for that. Okay, so hopefully we saw the difference of what we're doing. When we're just trying to find the minimum, we're trying to set this. Okay, kinetic energy is essentially 0 here. And again, we can work through it without any numbers because we have G and we have H's, right? And so we saw throughout the entire thing, masses go away, and we can solve that problem even without some information that we think could be necessary.